All right, so let's slowly get started. Good morning and good afternoon for those of you that are in Europe or Asia, the Middle East. My name is Stefano Galelli. I'm an associate professor at Cornell University, and today I will co-host this meeting together with Matteo Giuliani from Politecnico di Milano. This webinar is organized by the Multi-Sector Dynamics community of practice, and in particular by the working group on the use of artificial intelligence for multi-sector dynamics. We have two great speakers for today. However, before starting with the speakers and with their presentation, let me just say a few words about the multi-sector dynamics and our working group, particularly for those of you that are not familiar with the community. Of course, please be considerate and respectful. We will, during today's webinar, we will leave a few messages in the chat, and please use the chat for questions later. Now, what is multi-sector dynamics? It's very briefly the study of how complex built, natural, and socioeconomic systems co-evolve in response to change. And what we're aiming as a community to study is how we can advance our understanding of how different types of system feedbacks evolve, co-evolve in response to different types of uncertainties and in response to different types of stressors. The MSD community of practice represents an effort to accelerate developments of capabilities that are needed exactly in this domain. Something we stress that is particularly important is open science and growing a transdisciplinary workforce, and webinars as the one that we are delivering today go exactly in that direction. For those of you that are more interested in the MSD scientific vision, there's a report that was released in January 2022. You have the QR code here, so please feel free to take a look at the report. There's also a nice paper describing the MSD and its vision on Earth's future. And talking about Earth's future, there's also a special issue organized by different people in the MSD community. It's gonna close in December 2024, so there's still a little bit of time should you be interested in contributing to it. And for those of you that will attend the AGU fall meeting in Washington this year in December, there are multiple sessions also organized by our community. If you're interested, there's a website, of course, that you can refer to. If you want to join us, feel free to reach out to me. There are many other people involved with MSD. And of course, there's a join us button on the website. Now, talking about the AI in MSD working group, there are four main areas that we are, let's say, primarily interested in. First is to expand the breadth and depth of the data that are available for model development. Second is the use of AI to get a better understanding of complex model structures, including physics-based models, of course. Third is to support model diagnostics of coupled model chains. And finally, to expand the tools that are available to operate complex systems. And today's webinar goes exactly in the aligns well with the first theme. So expanding the breadth and depth of data that are available for model development. So with this, I will leave it to Dr. Matteo Giuliani to talk a little bit more about today's webinar and introduce the speakers. So Matteo, the floor is yours.
Thank you, Stefano, and good morning or good afternoon also from Italy, where I'm located. And about the topic of this webinar, as Stefano was mentioning, is aligned with this first research topic that the working group is interested in investigating, with a specific application field that is related to the analysis of extreme events, especially atmospheric extreme events that are impacting our society worldwide, and for which there is an growing interest and success in the application of AI and machine learning, with the challenge of dealing with extreme events that by definition are rare. And so we do have a limited amount of data for training our machine learning and AI tools. And so today we want to talk and hear about this issue and challenge, taking advantage of two presentations by Guido Ascenso from Politecnico di Milano and Etienne Plesiat from DKZ, Germany, who are studying somehow together and collaborating as part of a European project where we are dealing with the problem of advancing the characterization, detection, and forecasting, including also causal analysis and attribution of extreme events, etc. So this is recognized as one of the most important challenges in the field where we can build, and there are available tools for building very powerful pipelines working from the data collection to the modeling and generating outputs that are very relevant for multi-sector dynamics application in general, but this poor and limited availability of data, especially again when we are talking about extreme events, can represent a substantial obstacle for the development of robust instruments and tools. And so now I don't want to take too much time of introduction. I think the two presentations will showcase this issue and some of solutions that are out and are available to tackle this issue. So Stefano, I guess we can move directly to Guido for starting with the first presentation.
Sure. Thank you, Matteo. Yes, so I'll stop now, and Guido, please feel free to go ahead.
Yeah, thank you. I think you might need to stop sharing your screen first.
Yes.
Okay. Okay, thank you for the introduction. I'm with Ascenso, a postdoc in the lab where also Dr. Matteo Giuliani works. And my presentation today focuses on relatively simple methods to obtain more images of tropical cyclones. Some of you who may be versed in machine learning probably know already what that augmentation is. Some of you might not, but we're gonna look at that and also look at more advanced methods. So starting from basic methods for obtaining new images and then going to generative artificial intelligence. First of all, a little bit of context, although due to unfortunate events, it might not be needed to most of you. But my work specifically focuses on getting new images of tropical cyclones, which those of you who are from the US might know as hurricanes or perhaps typhoons if you're from Asia. Very devastating extreme climate events. They have killed over 700,000 people in the last 50 years and caused $1.4 trillion in damages and economic losses. There is many every year. There's one going on now that you're for sure seen in the news, Hurricane Milton in Florida. And they bring damages and deaths pretty much worldwide in any tropical region. The way we typically study and estimate and predict the intensity of a tropical cyclone, which of course is linked to its destructive power, is by looking at satellite images such as this one, and then using pretty old, to be fair, schematics to map the image to a known pattern. So for example, you would have a chart with similar patterns, and you try to match the pattern that you see in the cyclone at that moment with a known previous pattern, and then you assign the value of intensity based on that matching. This, of course, is very subjective and is very time-consuming. So in the last few years, with the advent of deep learning, we're trying to move away from this hands-on approach to towards a more automated approach. And specifically, convolutional neural networks are the model of choice for this task. I don't want to necessarily go into the details of how they work, but essentially they're deep learning methods, which is a family of artificial intelligence methods that take an image as an input, or perhaps also a sequence of images, and extract features that go in progressive complexity in terms of the semantic content. So for example, at the beginning, the network might be looking for simple edges, small segments in the image. And then as the network processes the image, it starts to recognize more advanced semantically complex features. For example, the eye of the tropical cyclone, how well defined is it, how central it is, etc. And then it uses these features that it extracts to make a prediction on the intensity of the cyclone, which in this case is given by the wind speed. So the maximum wind speed of the tropical cyclone is taken as a measure of its intensity. However, these models require very large amounts of data, typically in the order of tens of thousands or ideally more of images for each type of tropical cyclone. But the data that we have available for tropical cyclones are quite limited, mainly by the fact that these events are quite rare, especially the very intense, strong ones. And unfortunately, these are the ones that we want to predict the most because, of course, the higher the intensity, the more destructive it is. So we care mostly about predicting the very high intensity tropical cyclones and not the weak events. But because the stronger ones are also more rare, we have a data imbalance problem, which is displayed here, where the number of tropical cyclones for category 5, the number of images for category 5 tropical cyclones are many order of magnitudes lower than for weak tropical cyclones. And naturally, if you train a machine learning model with this data that are so biased and so imbalanced, what will happen is that the model will learn to predict weaker tropical cyclones regardless of the input. So this is clearly not something we want. Just a note here that I'm talking here about classes, about dividing the dataset into classes of intensity. This is mostly for illustration purposes to make it a bit clearer, but the problem that we're dealing with here is purely regression. So the task that the model is asked to do is to output a number, which is the wind speed of the tropical cyclone. And then based on the number, it will fall in one or more, in one category shown here, but the task is regression and not classification. To allow more images to be available of the rare tropical cyclones, researchers typically use data augmentation techniques. And these are not unique to study tropical cyclones. In fact, they've been around for many decades in the field of computer vision. And they're essentially a collection of pretty basic transformations of data, of images, that generate new, slightly changed images. For example, you could take an input image and rotate it by a certain amount of degrees. You can crop it, you can make it more blurry, you can change the saturation, you can translate it along one or more axes, etc. And the idea here is that you then treat each of these transformed samples as new samples. You ignore the fact that, of course, they're going to be highly correlated with the original samples, and you use them as additional samples to increase the dimensionality of your data set. But in the field of, in their application to tropical cyclone intensity estimation, there haven't been many guidelines. There's been a few papers that have done this with the images that I showed before of cyclones, but without really following strict principles. And so in this piece of work, we sought to investigate what is the best way to perform data augmentation for this task. And the framework that we derived is very simple and flexible enough that it really can be applied to many different types of domains and is absolutely not strictly related to tropical cyclones. So 3 questions that we sought to answer. First, which transformations should you use? We saw a few basic ones, but are all of them valid? Should you avoid some of them? Should you prefer others? How much augmentation is needed? So should you create 10 million copies of each image? Should you only copy them once, 5 times? Is there an upper limit, a lower limit? And then number 3, which seems like a trivial question, is should you use this data augmentation to rebalance the data set or not? In other words, should you do more augmentation for the classes that are less represented, or should you just increase the size of the data set in a flat kind of way? So first of all, to answer the question which techniques you should use, there are 2 governing principles regarding data augmentation that must always be preserved. First of all, data augmentation techniques should be label preserving. What this means is that if you have an image that has a label assigned to it, for example, the image on the left will have a certain intensity. In this case, it's 110 knots, which is a measure of wind speed. Any augmentation that you do should preserve the label. So if I do the transformation, the label of the image should not change in any way. But of course, you see here that if I adjust the brightness of the image, which is a standard dot augmentation technique, this is not true. The label is changing now because the color of the pixel is changing, and therefore this doesn't correspond to the same type of event. And so this type of augmentation is not usable for this purpose. Second of all, the transformations need to create samples that are representative of real variations in the data. So for example, a tropical cyclone is a system that rotates, and therefore rotating the image by a certain amount of degrees seems logical. Same with flipping the image, because you can think of it as a special kind of rotation. But then there's two types of augmentation techniques that are a bit controversial. First of all, translation, so translating the image along one or more axes. I'm aware that these images at the bottom all look like they're exactly the same, but they have slight deviations from the original. So should you translate horizontally or vertically the image, so decentering it a little bit? Well, the argument in the literature is that you shouldn't do that, because as you see, the images that are used for this task are usually centered on the cyclone. And so if you translate the image horizontally or vertically, you're decentering it. But then if all the other images are centered, this is not a variation that is representative of your real data. And so you should avoid translating. Likewise, random erasing is a technique that has never been applied to tropical cyclone estimation. It consists in essentially just adding a band or more bands of randomized pixel values. The reason it has not been applied to this field is perhaps also because it's a relatively new kind of data augmentation technique, but also because it doesn't immediately seem like it would be relevant given the images that we see. We don't really have occlusions. For example, in other tasks in computer vision, when you're detecting pedestrians, for example, there might be occlusions, and therefore adding these occlusions in the images seems intuitive. But it's the same applicable for tropical cyclones. So to investigate this, we put together a relatively simple pipeline. I know it looks a bit complex, and I'm not going to go in the details of every block, but I promise you that the pipeline is really quite simple to understand which techniques work best for this task. And essentially, all this pipeline does is it takes all these techniques that I mentioned before, uses them all together to create augmented data set, and then trains a convolution on your network, those artificial intelligence models that we saw earlier, and obtains a certain amount of performance. We then remove one technique at a time and measure how much the performance is degraded. So if we remove an augmentation technique from the set and the performance improves, that means that that technique was detrimental and should be removed. If the performance decreases after we removed a technique, it means that that augmentation technique was actually beneficial and it should be reinserted into the set. And essentially, we go through this simple loop and we search for all the techniques that are beneficial. And what we found is that actually all of them were beneficial, all of them were useful, including the two that I mentioned that might be problematic. And this brings me to a very important point that I wanted to highlight, which is that when you do augmentation, you should be mindful of the characteristics of your data, and you should really know what your data look like. Because random erasing actually does occur in satellite images quite often. For example, you see here, there's some kind of sensor error type thing that really looks like some kind of random erasing like the one that I showed before. So this is, in fact, a naturally occurring variability in images, and therefore this is effective because it mimics more variability in the images. And as for translations, the argument was, well, the images are centered on the cyclones, so you don't want to translate them at all. But actually, it turns out that the way the images are centered, which again, I'm not going to go into great details about here, but the way the images are centered is prone to error that is larger for weaker tropical cyclones. Essentially, this is due to the fact that if the cyclone is weak, the eye of the cyclone is not very well defined, and so it's not that easy to find its center because you literally don't see it. And therefore, we have pretty significant errors in the centering of the images. And therefore, if we use translation as a data augmentation technique, we're mimicking this uncertainty and we're perhaps even compensating for it. And in fact, if we look at how important translation as an augmentation technique is for the different categories of intensity of tropical cyclones, we see that it is in fact most beneficial for the weak tropical cyclones. What this table shows here is the percent error reduction in each category of intensity if random erasing is used. And you see that it's mostly beneficial for those winds for which the center is harder to localize. So again, important, very important when using data augmentation to truly know your data, truly know the sources of variability in the data, and then try to mimic them using ad hoc augmentation techniques. Second question was, how much do you want to augment? The obvious answer is, well, you want to augment the data set so that it's perfectly balanced. However, this means that for the very low populated classes, you need to do a lot of data augmentation. M here represents the number of times by which you need to upsample, so increase the dimensionality of that class. So for category 5, that means we would need to generate 280 copies of each image of category 5 hurricanes. And that's a lot of data augmentation. So presumably that's too much. So we're not going to be able to get to a perfectly balanced data set. But is there also a lower bound on this M value, on the amount of times we want to upsample each image? And so to answer this question, we simply tested a bunch of different numbers of M and saw where the line was. And we got to this graph, which immediately tells you that upsampling everything by 100 times is definitely not going to work at all. It's so out of scale that I had to crop it out. You see here on the y-axis, the root mean squared error. You measure knots, so again, wind speed. So you see that augmenting too much causes the model to not be able to learn basically anything. So absolutely not usable. Not using any augmentation, which is the blue line, kind of works for weak tropical cyclones. In fact, it seems to be the best, but then has very big errors for the very high intensity tropical cyclones. Again, because there's very few samples of those cyclones. And so the best compromise that we found was for M equals 50. So this means we're upsampling the data set for each class up to 50 times. And for M equals 50, we have the lowest error on the highest intensity tropical cyclones, corresponding with also the lowest error overall, over all averaged categories. And the resulting data set looks like this. And you see that it's rebalanced, except for the category 5 hurricanes, which again, to rebalance also this class would have required a higher degree of augmentation, which however, then would have been detrimental for everything else. So it was not feasible. And finally, what we wanted to test was the third question, which seemed trivial. Should you rebalance the data set like we've done here, or should you just increase the dimensionality of the data set by 50 times for each class? Because, for example, for this class on the left, you can see that it was not upsampled 50 times, but a lower amount, enough to bring it to equality with the others. So this class, for example, was only upsampled 1.3 times, where other ones were upsampled 50. So should you apply flat 50, so upsample every class 50 times, or should you apply an adaptive amount of data augmentation trying to rebalance the data set? And the answer again is pretty clear here. You definitely should use data augmentation to rebalance the data set. But as I mentioned, this is not as trivial a question as it may seem, because the tendency in the literature is to not do this, because it might be trickier to rebalance the data set, and it might be easier to just apply a flat amount of data augmentation. But the advantage of rebalancing the data set here is quite apparent. We're comparing here 3 scenarios, what I call best augmentation, so it corresponds to this data set where it's rebalanced. No augmentation at all, so the original data set that is very imbalanced. And then what I call naive augmentation, which is what I was referring to before, which is the idea of just augmenting every class by the same amount, for example, by 50 times. And you can see that this naive augmentation is better than doing no augmentation at all, simply by virtue of the fact that you're adding more data. So you're expanding the size of the data set. However, it's barely better than not doing any augmentation at all, because the data set still is heavily imbalanced. And so the model that you're using behind the scenes is incentivized to still predict the weaker classes. Whereas if you use a rebalanced data set with the best augmentation scenario, you don't have this problem of the model being incentivized to predict one class or the other, and therefore it makes it more able to do the task that it's trained to do. So answering the 3 questions, just as a quick recap of this, which transformation should you use? All of the ones that we tested turned out to be good. So rotations, flipping, erasing, and translation. And erasing and translation were particularly interesting because previous research discouraged their use, but we found that they're actually quite beneficial for this task. How much augmentation is needed? This is heavily dataset dependent, but for us, augmenting each class by upwards of 50 times worked best. And then should you augment the dataset in a way that rebalances it? Yes, it's just superior. Now, this brings us to another question, which is what about generative AI? I'm sure many of you, perhaps all of you, have heard in the last few years of these models that create very realistic looking images. There's several that are available. There's Dolly and Stable Diffusion, most famously, and Midjourney. Can they also be used to generate images of tropical cyclones? In other words, can we use these models instead of the traditional data augmentation techniques that we used in our work? We have started to investigate this question in our lab, and the results seem to be promising, but with a question mark. For example, here we see 2 examples of wind fields of cyclones. These are not tropical cyclones, so they're not hurricanes, they're extratropical cyclones, but for the sake of the seminar, just think of them as almost equivalent systems. They're not, but they're similar enough. And so the wind fields here on the left, on the right, seem to be pretty similar. And if I asked you to tell me which one is fake, so generated by AI, and which one is real, the climatologists among you will tell me immediately, but those of you who are not so versed in climatology might take a couple of minutes. I'm sure if I gave you enough time, all of you would reach the correct answer, which is that the one on the right is AI generated. But the distinction is not immediately obvious. And this brings us to one of the main concerns with using AI, generative AI models for generated synthetic fields of tropical cyclones, which is, can we trust the generated images? Yes, they look very realistic, but they look very realistic to us. And the question is that we are not fully sure what features the machine learning models is going to look at. We saw in the beginning that the convolutional neural network that is used for estimating the intensity of tropical cyclones typically looks at features such as the eye of the tropical cyclone, maybe the rain bands, etc. But if we use images that have very small and maybe undetectable by us, but wrong features, such as the ones that are on the right here, there is a real possibility that the model would then learn a pattern that is not actually realistic. And so what this means is that we need to determine a way, we need to find a way to determine if the generated images are truly realistic. And we need to do this in a quantitative way, not qualitative. It's not enough to look at these two images and say, yeah, the one on the right is pretty much similar to the one on the left, and therefore it's okay. We need to quantify the differences. But as it turns out, that's quite complex. And it's one of the things that we are struggling the most with is quantifying the similarity between AI-generated images and real images of cyclones. And my main takeaway from this is that, yes, generative AI models are promising and they might be the way forward, but not for all use cases and probably not right now. And for the generation of new samples of tropical cyclones, it might still be easier to just use the traditional techniques that I covered before. So rotations, random erasing, translations, etc. Just because they circumvent the problem of knowing if you can trust the images or not. And that's it from me. I reported here just a couple of quick references. The one at the top is the work that we did with the augmentation techniques. And thank you for your attention.
Thank you very much, Guido. For the question, we would wait after the second presentation. So we'll do question time at the end of the webinar. In the meantime, however, if you want to start posting some question in the chat, we can start collecting them and then we can direct those to Guido when we open the question time. Say that, I guess we can transition to our second speaker, who is Etienne Plesiat from DKZ. The topic of the presentation and the talk is changing now. So we stay in the problem of data, of the data challenge for extreme events, but we move to temperature data, temperature extremes, and the time scale is also changing. So the idea is to have better data to better understand longer-term trends in temperature. So Etienne, if you want to share your screen, the stage is yours.